Thanks very much. It's a great pleasure to be here. I've never been in this corner of the world before, so very exciting. And so I'll dive right into this. I've got quite a lot of material, and it's a big subject, right? It's climate policy. I'm going to try to approach it in a pretty broad manner, from the physics to the sociology. So this is, I looked up the temperature in the Tucson area. This is the forecast. It's looks like it's going to get another 10 degrees warmer, that is Fahrenheit. It's already warm. I don't know if if the cactuses will start to wither or what will happen. We're going to be talking eventually about the costs of climate change. This is one of the places. It could become uninhabitable eventually. What would be the cost of that? Is that the end of the world, or would people just move and get on with it? Well, that's the kind of questions we'll be thinking about. At the moment, the brakes are off the wheels of history. I like that phrase. I read it in a very British commentary about American politics. And I'll be talking about both the climate crisis and other environmental problems, but also a little bit about growing inequality, polarization, a bit of a crisis of democracy, but all the time thinking of the social cost of carbon. The social cost of carbon is the cost of emitting 1 more ton of carbon dioxide. And this is not a cost like other costs. Right? You go and buy a suit, there's a cost. What's the cost of emitting a ton of carbon dioxide? Of course, 1 ton doesn't make any difference, but a billion or something. It changes the course of history, and we have to try to understand most of the costs are going to be in the future, and we need, it's a sophisticated and difficult endeavor to figure out what the cost is. But first, let's think broadly about which planet to live on. We speak a lot about warming, and there's a concept you need to understand. It's the global average temperature. It is the average of every hour of the day, every day of the week, and every week of the year in every place on Earth, equally weighted. Above the oceans, just above, because it's at the surface. And here, it's at the elevation that it is here, so the elevation varies. Right? Earth has roughly 15 degrees centigrade measured that way. The main alternatives, if you want to move, are Venus, which has 460 degrees, and Mars, which has minus 65. Of course, the distance to the sun is one of the main factors deciding this, but also the amount of atmosphere you have and the character of the atmosphere. So the moon, which is roughly the same distance to the sun, is much colder. It's about minus 23 on average, although the average is a strange concept because it's never minus 23 on the moon. It's always either minus 170 or plus 130, depending if it's day or night. And then it switches brutally fast. So that's probably not a nice place to live. I've kind of decided I'm staying on Earth. It's a statement. So let's look at the temperature around here. And let's go back to 2008. 2008, for me, seems recent. I know some of you might think that's a long time ago, but at that point, we had about 0.75 degrees of warming. Right, and if you look at this figure in detail there, you can see that it was stagnant for the last 10, or in fact, almost 30 years, if you look at that dotted line there. And that's what some of the climate deniers were saying at the time. that this whole climate change thing is a bit of a hoax. There hasn't been much warming since 2030. I wonder if I have a laser point. Yeah. So there hasn't been much. They chose, of course, a point that was a local high and then a point that was a local low. But they said that there hasn't been much warming for 30 years. Then there was a bit of a jump. But then in 2021, they were kind of saying the same thing, that it's not really growing at the moment. And now that problem has kind of been solved because it's grown quite a lot. And the last observation there is actually not a yearly average, it's a monthly average. It's for January 2025. And now even the climatologists are like, we don't quite know what's happening. The rate at the moment is sort of unheard of fast, and it's become a problem that climatologists are discussing. There's a cycle, the ENSO, and in Niño years it gets warmer, and Niña years it gets colder. And here was a Niño event, so that explains part of the increase. But we are now, since January 2024, in La Niña. So why it's rising like this is unexplained. And there's about 0.2 degrees that are currently being discussed. And they're thinking that perhaps there's something that is changing in the way clouds at different altitudes are behaving. So there's perhaps a new feedback loop that they didn't know about. Now, I thought I'd tell you a bit about what all this is. So we keep on continuously, the sun shines every day like it does, particularly here. Why doesn't the Earth get warmer and warmer? We get more and more sunlight coming in. Why don't we just get warmer and warmer? Well, we also emit. We also are a body that radiates, the Earth is, and so there is long-wave radiation going out, just like there is shortwave light radiation coming in. So this heat goes up that way. And according to Boltzmann's equation, this is a fourth power of temperature. So if it just gets a tiny bit warmer on Earth, the radiation out gets a lot more intense. And there's a spectrum. There's a lot of different wavelengths. So we'll come back to the wavelengths later. But now, look at these things here. These are molecules here. That's methane or the dinitrous oxide. That's carbon dioxide. Well, these molecules, when they are hit by radiation of a certain wavelength, they get excited. This carbon dioxide, you can see it looks like this. And if it's hit by a 15 micrometer wave, it starts to do sort of wobble like this. And if it's hit by a 4.3 micrometer wave, it starts to do this, right? And this excitement picks up some of the energy, and then it stops being excited and re-emits a photon of energy, but in a random direction, because these molecules are whirling around. So if it sends upwards, then nothing much happened. But if it sends down this heat, then it stopped the radiation, and so the cooling, what we call global warming, could also be called delayed cooling. It's Earth trying to cool itself, so to speak, and that process is delayed by these molecules. I studied a lot of chemistry in my school, and this was in England. I don't know, have you been to England? It's a really strange country. Anyway, their pedagogics is sort of harsh. So the teacher had spent a lot of time. We did a lot of chemistry. That was interesting, a good part of it. He was explaining the molecular structure of carbon monoxide and carbon dioxide, and explaining why carbon monoxide is so poisonous and carbon dioxide not dangerous at all. So I gave a lecture in Uruguay. This is the Minister of Finance in Uruguay there. And after the lecture, it was a bit of a smaller room and very full. And there was a meter for carbon dioxide on the wall, and it was 4,374 parts per million. You know how many parts per million there are in here? It's 440. It's 440 everywhere. I'll talk about that in a moment. But at the end of this lecture, it will be about 1,000, maybe. And I calculated quickly here, this room is about 1,000 cubic meters. So there would be about 2 kilos of carbon dioxide in here. 2 kilos. Think of that as a weight. 2 kilos. And half of that comes from the atmosphere outside. Half of it is your breakfast that has been burnt. Literally, chemically burnt through our bodies. So 2 kilos of carbon dioxide, that's about 10 million, or 10 trillion, if you like. So those are the number of molecules. So far, maybe just 5, I should say. Right, in here, 5 trillion molecules. And each of these is prone to doing this and that as well. That's another. They can do all kinds of things to sort of stop the heat from radiating out. So here's the most long-run diagram I'm going to show you. It's 400,000 years. You know, economists, there's all kinds of jokes about what economists think is the long run. Well, this is definitely long run by economic standards, right? It's 400,000 years. And it's actually looked the same for 800,000 years, roughly. The carbon dioxide has always, so to speak, for 800,000 years, been between 180 parts per million and 280 parts per million. When it's 180, we have ice ages. Where I live, we had about 3 kilometers of ice. Yes, 3 kilometers. Land is still rebounding. We don't have a sea level rise problem. Locally, land is rising faster in Sweden than the sea. So actually, the sea is, receding. Now, suddenly, in these periods, humanity as we know it, and not just like cell phones, but the whole of humanity since the ancient Greeks and so on, has evolved in this epoch here. I mean, 1 millimeter here is an epoch, right? It's quite a long time. And suddenly, kaboom, we just went from 280 to 424, which is the reading today. And you might be wondering, I hope you're wondering what's going to happen. One of the stark facts is that we don't know, right? Because we haven't done this before. It's a once-off experiment. And it's a very large experiment. We can look at an even longer time horizon. Now we're here somewhere, right? We have had high levels before, but I mean, 50 million years ago, for instance, they have found fossil alligators on the North Pole, so they know that there were alligators on the North Pole. Things were quite different. Sea level was about 50 meters higher than it is now, so London was gone, and Bangladesh and quite a few other things didn't exist. So things were very different. We don't know if they had thunderstorms, cyclones, tornadoes, fires. We don't know that because it's too long ago. Right? We tried to do research on these things, or people tried to do that, but it's hard. So it's an interesting experiment we're in. That about climate. I thought I'd say something else before I get on with more climate about the economy and the world economy. And we live in a world with a falling labor share of GDP. I think that's important. But, I mean, we'll look at a few other figures that sort of say something slightly similar. I borrowed these from Simon Johnson, who visited us recently in Gothenburg. We speak a lot about how much better, how the economy is growing and how much better everybody's doing. That probably applies to many of us in this room. But if you look at high school graduates and high school dropouts and even people who have a little bit of college, they haven't actually seen any real increase in income for about 50 years. Whereas people with a graduate degree have. So there's an increasing inequality. This applies to large parts of the world, in fact. There's also an international restructuring of the world economy. So if you go back to the 18th century, China and India were dominant in world manufacturing. They sort of disappeared. Sometimes they were made to disappear. England kind of burnt millions of looms and things in India in order to be able to sell their own textile products. And English manufacturing grew as a share of global manufacturing, and then the US did. And that's up to 1913. So what do you think happened after that? I want you to think. You don't have to answer, but it's pedagogical to think before you hear. So this happened. The Chinese would say that they reclaimed their natural place. They are about a quarter of the world's population, and now they again have about over 30% of global manufacturing. The US has declined. English manufacturing has completely disappeared. India, there's a slight growth, but nothing of the scale of China. And there's a few other countries I have, Japan, Germany, and a few others, they have about 5% each as well, so they're not on that diagram. This is quite a large restructuring. Has some important effects. And there's also an interesting difference between China and a lot of other places, in that you can see here, this is average hourly wage in the US and in China, and in Japan and the US. And this is China down here. And you saw how they have grown in manufacturing. It's not that they're not productive. They are productive. But they're not being paid, right? So basically someone, that is the Chinese state, is accumulating a very large surplus, which they are using very strategically for all kinds of purposes. And you read about that in the news every now and then. So back to the environment. In addition to the climate change, we have a number of other problems. It's hard to quite list exactly which are the most important, but we're in the midst of, we're losing species, we're losing biodiversity at a rate that has been seen 5 times before. The last time was 65 million years ago, but there's a number of other events in the fossil record when they can see that the diversity of species has decreased. That's happening at the moment very fast. Perhaps related to that, or partly explained by the fact that we're digging up a lot of toxins from the geosphere and putting it into the biosphere, for instance, through burning of oil and coal. We're making new synthesized chemicals, that we sometimes don't know the effect of before they're spread all over the environment. We're acidifying even the oceans, the oceans are big, so that's quite something. And there's disturbances to all kinds of other kinds. One of the results of a combination of all these things, but particularly the acidification of the oceans and the rise in temperature, is that we're going to lose the coral reefs. How many of you have been diving on coral reefs? Anybody? I suggest that the rest of you who want to try to do that soon, because, well, the best estimates is, I mean, I'm not a coral reef ecologist, but the ones who publish in Nature and Science, they say that they won't stand much more than 1.5 degrees of warming. The last few times I have been on coral reefs myself, recently, the supposedly best reef outside Kenya, it was a very sad experience. It was completely bleached, and worse than that, it definitely started sort of cracking up and dying. So, again, is this, well, we'll come to this. What's the cost of this? There are other impacts. I'm trying to get to the impacts of temperature on various things. One of my good friends in Delhi, Somanathan, he works at the Indian Statistical Institute. He has all the statistics from everywhere in India. And they did studies looking at what happens on warm days. That is, we have to be careful methodologically. It's not quite the effect of climate, it's the effect of temperature, it's the effect of warm days. Of course, with the warming climate, you get more warm days more frequently. So it's still very closely related. And on warm days, I mean, if you are an agricultural worker in India, in the fields, on hot days, you need to drink something like 6 liters of water. It's actually hard to drink more. Sometimes the quality of the water is not that great, and there's arsenic or something else in them. It's very common in the Calcutta region and in the whole of Bangladesh as well. So also for that reason, you can't drink any amount of water. And then people just sort of faint and die. It's also, of course, for the plants, it's not good either. So agriculture is quite obvious that it's hit. But they found evidence in every industry, in garments sewing, in steel making, in diamond polishing, in carpet weaving, and so on. The warmest days, productivity just plummets. And this, even people are paid by the piece, they're not being paid if they don't work well. So there's definitely an incentive to work. Right? But it's just, you get to the limits of human endurance. Then the question is, what can adaptation do? Is this cost temporary? Or would it permanently be a cost? And so this is borrowed from Michael Greenstone, a recent paper in AER, where he shows roughly the same thing for India, but he also shows that in the US, nothing much happens on warm days in that respect. So, of course, to some extent, particularly for people who work indoors, in rich countries, you can have air conditioning even for workers in factories. You don't have that in India currently. You don't have it in most places in the world. Could we have it everywhere in the world? Well, one of the problems is that, of course, the amount of energy needed would make climate change worse unless we had new technologies, which, of course, we should have. So there's likely to be a distribution of climate damages. So it will be much worse in really hot places than in cold places. And many currently cold places may even benefit, so they say. We don't know that, but I mean, it's conceptually possible. like my country, the north, you might argue that it's a place that is too cold. So if it gets a little bit warmer, maybe that would be nice. Maybe. That's not certain. If these processes happen very fast, there's no time for, we will have the wrong tree species and the wrong soil bacteria species and everything else, and then suddenly the climate is warmer. That might not be great for agriculture. It's an experiment. Now, so maybe the rich will do fairly well. Though, of course, if things get too bad in the global south, people will start to move, and we can see that the world is agonizing a lot about the hundreds of thousands and the odd millions who are migrating today. If billions try to migrate, it will be different. So, what should we do about this? This is just for carbon here, carbon emissions. And you can see carbon emissions have been almost a straight line. Here we had OPEC. I don't know if you heard. There was oil crises in the 70s, and they formed a cartel called OPEC. There were two crises. And there was the breakup of the Soviet Union, and there was the financial crises, and then at the end there's COVID. And you can see each time there's a tiny little blip. But we have not got to this curve to stop growing. So let me check again. Let me be the teacher here. What's the goal? Do we want this curve to stop growing? Yeah, exactly. Thanks. So no, we want the carbon content of the atmosphere to stop growing. This is a stock problem. So emissions have to go to zero. For this, we want the stock to stabilize, not the emission curve. For the stock, this is like a bathtub. You want the bathtub to not run over. It's not enough to reduce the amount of water running into the bathtub. You have to turn the water off completely. Are you with me? So this is the plan. That's what we need to do. If it wasn't so serious, it would be kind of funny. Right? And it doesn't look like it would be possible. And I have two questions there. Is this possible? And will we succeed? I'll stick my neck out and I'll say yes, no to those two questions. It would be possible. We will not succeed. So let's compare with peak. Who's heard of peak oil? Nobody? One person. Congratulations. So peak oil was a theory that the petroleum geologists said that we've used up most of the resources of oil, and so in the future we're not going to find so many new resources, and they will be less and less useful and more expensive, and so we're running out of oil, basically. Suppose we would have had that problem instead, running out of oil. What would have happened? Now let's see, how many of you are economists? There's a few economists. You know what would happen. Right? Price of oil would go up. Anything else? Would that be the end of the world? There's lots of things that are expensive. I mean, gold, rhodium, californium, and diamonds are all much more expensive than, and so we don't have so much of them. Is that the end of the world? No, we don't use expensive things so much. I mean, a few rich people have some to display their wealth, but, and we use them for some very special industrial purposes where they're uniquely valuable. So we would just use less oil. That's it. We would use more solar cells and wind and nuclear and efficiency. Next question. It really wouldn't be, I think, the end of the world, or there'd be some restructuring, of course. But, well, like AI or something else, it's, things, a new industry, and an old one dies, and restructuring. So the question is, why can't we just emulate that? Well, there's a difference. If the oil price just goes up of its own, and everybody knows it's going to go up, and then, well, people say, well, oil price is going to go up, I'm going to build solar cells, I'm going to build willpower, and so on. So then the economy just adapts, and there's no question. But now it's not, we're not running out of oil, coal, and gas. Instead, we're running out of something slightly more subtle, which is the sort of the ability of the atmosphere to be a waste paper basket for our carbon dioxide. Right? The assimilative capacity of the atmosphere for carbon dioxide, that's the scarce resource, and there's no owner. And since there's no owner, the price won't go up. The price is zero. It's free. And so instead, if some politician is going to come along and say, I'll put the price up through a tax, then that politician might not be credible. There'll be other politicians who say that he's an idiot, vote for me instead. And so it's less certain, and so industry doesn't know if they're going to build all the alternatives because they don't know if this actually is going to get more expensive or not. And the politicians who try to do this, I mean, in some countries there's some efforts, but it's more difficult. Anyway, now we'll talk a little bit about the social cost of carbon, because one of the problems now we face is, okay, so we should raise the price of carbon. That's everything from gas taxes to electricity prices, or just put a social cost of carbon on, and then let that work itself through the economy. But now we need to figure out how big is the social cost of carbon. How high should this tax be? And so there's a debate, and there's a whole sort of history of this. There's hundreds of people who model this and debate this issue. And I'm going to tell you about a bit of that, a history of those debates and so on. Very recently, or well, it's already 5 years ago, we published an article here where we somewhat audaciously claimed to know better than the Nobel Prize winner Bill Nordhaus. So I'll tell you why this happened. It kind of happened on October the 8th, 2018. On that day, two things happened. The IPCC special report came out. The IPCC is the United Nations body which does research on, how bad climate change is going to get. And they said that we really need to make sure to stay close to 1.5 degrees because 2 degrees will be terribly bad. On the same day, the Swedish king gave a nice Nobel Prize to Bill Nordhaus for this model called DICE, which analyzes what happens and what we should do about climate change. So he got this prize for this model, and he has really single-handedly started the debate and in some sense curated the debate. He has made his model accessible on the internet, and everybody, like me, have been able to go in and change parameters and play with it, which is a really exemplary way to to act as a scientist. There's a lot of scientists who keep their models as black boxes instead. But the conclusion of that his own calibration was that 4 degrees was optimal. This is, and in fact, I was interviewed on this. I had a kind of personal memory of being on television and saying, well, you know, I'm glad that Nordhaus got the prize. It's nice that, you know, climate, and I like the model and everything. But I think that he is wrong about 4 degrees being optimal. And members of the Nobel Committee called me and like, what do you mean 4 degrees? He's never said that. Where do you get that from? And I said, well, from his publications. And so this is what he described as business as usual, and this is what he described as optimum. It gets to 3.5 by the year 2100, but you can see that it's going up, and if you look at the details, it goes past 4 degrees sometime in the next century. So there's a problem here. Is 4 degrees optimal, or is 1.5 degrees optimal? And related to this is, what's the tax level going to be? How much should we try to do about climate change? And so we have our own version of DICE, and we have made a number of changes. Some of these are changes where we think that he was wrong, and some of them are ethical choices where there is no right or wrong. It's just a choice, right? But the damage function, the carbon cycle, the energy balance, and where do you see the list here? I'll go through each of these. How am I doing on time, by the way? Have I talked for half an hour?
40 minutes.
I've talked for about... Yeah, that's okay. I think that's good. But still, each of these things, you know, we can talk about each of them for about 4 weeks. So the damage function, that is, how bad is it that the temperature rises? We have an expert right at the back of the room there. Hey, Derek. So the first time Nordhaus was writing about this sometime back in the late 80s, there were no damage functions. He needed to make one up. And that was a logical thing to do, and he kind of looked at a list of, you know, I can imagine, I don't know, but I mean, you know, what sectors would be hit and what damage might there be, and he made up some number. And then published that. And then a few years later, he needed to update DICE, and then he did the same thing. And then more and more studies were being made. Every time a new analysis was made, it was sort of the average of all the old ones and some new ones. So one of our critiques is that all the latest averages, there's like 3 people doing this, like Nordhaus himself and Thal and 1 or 2 more. And so they were citing each other, and they had set multiple estimates each, and then they were taking average of these. You do this once, and then next time you do it, then you've got both the first estimate and the second estimate, and the average of those, that was the third estimate, that becomes the fourth estimate. And in the end, we found this isn't the right way to do a meta-analysis, because there's, well, you could call it double dipping. It's not really the technical term, but there was a sort of a too much reliance on a few people. And so we did all kinds of things. There were multiple other problems of heteroscedasticity and of not weighting by variance and other things. So here are, anyway, some of the damage functions that are around. Here is one by Thal, for instance, and this is one that was DICE 2013. They have a damage somewhere between 5 and 10% of GDP for 6 degrees warming. 6 degrees warming is described by most natural scientists as Armageddon. So I mean, we actually, when we work on this, we do a lot of sophisticated econometrics. Now I'm just trying to sort of entertain with saying that this is strange, that very low level here. Our own estimates here, which are just averages of the published estimates, they're considerably higher. Now, this is a very big area of work. Bigger and bigger teams are looking at this, sort of like my friend Samanathan, who I said was looking at different industries in India. That kind of work is going on all over the world. It's being assembled in more and more sophisticated ways. And Derek at the back there is writing a wonderful paper on how we should think about this, right, systematically. That's just on the damage function. Now, there's also a lot of natural science in this model, and I think in the interest of time, I will skip that. Nordhaus has basically also changed his model now, so we now agree. I mean, so there was a problem in a former version of the model that is now solved. But I'd like to talk a bit about the ethics, because most of the problems of climate change will befall on people way into the future. In 50 years, maybe in 200 years, 300 years. So how do we compare their costs with costs and benefits today? Well, we do this with discounting. And discounting is numerically very powerful, right? Because the simplest idea is that you put $100 in the bank, and if there is interest and growth in the economy, at the end of the year you have $103. So in that sense, 103 in 1 year is the same as 100 today. Now, if you have 3% growth, it takes 24 years before you got doubled. And in 100 years, you got 16 times. I usually joke about me trying to eat 16 times more cheese and drink 16 times more wine, and that's hard. But I'll come back to that later. The simplest formula we have for thinking about how big the discount rate should be is this one here, called the Ramsey formula. It has a delta there first, which is utility discounting, which is just how much we couldn't care less about the future. Our rate of impatience, or utility discounting. Most people agree it should be low. Some people think it should be zero. Many famous philosophers and economists have such a said. But then on the other hand, there's a small likelihood that we'll be hit by a sufficiently big asteroid so that Earth is destroyed. And for that reason, maybe a tiny delta would be motivated, because it would be a pity to save a lot of money for after Armageddon, right? Now, if we cause Armageddon ourselves, that's endogenous, so that shouldn't be counted, right? But an exogenous Armageddon is a good reason for having a delta. Then you have eta and g. G is the growth rate. And if we have 3% growth rate, which quite a lot of low-income countries have in the world, then they will be twice as rich in 100 years. And if you see a lot of dollar bills lying on the floor, I'm going to show you, you know what dollar bills look like. If you see a lot lying around, you know you're in a place where people are rich and have so much money that they wouldn't bother to pick them up. So it's kind of obvious, if we think of a $100 bill and we could give it either to a poor person or to a rich person, it's going to give more utility if we give it to the low-income person. I hope you all agree. How much more utility? Is the poor person going to be twice as happy as the rich person would have been? Well, that sort of is the thinking that is going to decide the size of eta here. That's called the marginal elasticity of utility with respect to consumption. Now we can make this formula a lot more complicated. And some of us think this is both important for humanity and a lot of fun for the maths. So there's a lot that can be done. I'll be talking about a few things, particularly what happens if you have different growth rate in different sectors, for instance, and a little bit about the limits to growth. And so this formula, try to keep it in your mind and think about that. The first paper I wrote about this was this one in 96. At that time, Nordhaus said that the social cost of carbon, that is the optimal carbon tax, was $7 per ton. And we said 50. Nowadays he says 50 and we say 200. So, quick summary there. In this article we said, because growth is very important, as you could see from the discounting there. So this was a paper where we said, well, suppose that there are limits to growth. So we have normal growth now, 3% per year, but it sort of stops when we get 10 times richer, which will be in 60 years or something, quite a long time away. So we did that. We calculated what would happen. It turned out that the social cost of carbon would be like a lot higher. Right? That's why we got this much bigger number for the social cost of carbon. Because in the future, people won't be so humongously rich that the costs don't matter at all. So it all hinges on what we think the future is going to look like. If you think that the future, people are going to be hundreds of times richer, then we don't need to bother about leaving them intact ecosystems. They'll have so much money, they'll figure it out, if that's possible. But that's basically the thinking. Here in this paper, we had limits to growth, so the world only got 10 times richer. And that, well, there were several things in this paper. We also had divided the world up into rich and poor. Because you saw that little eta there, how much more we care about the poor than the rich. But so if we don't care more about the people in the future who are going to be rich, then logically we should care a lot about the poor today. And the poor in Bangladesh, and it turns out that the poor in Bangladesh, even if they have 3% growth, they're still going to be poor by our standards by the time they get drowned by rising sea level. So they are actually poor people who are going to be. So if we didn't care about the future rich people being hit by climate change, we should care a lot about the poor people. So this is where the ethics, the mathematics of the ethics, comes into what the social cost of carbon, how much it costs to emit a ton of carbon today, can go from 70 to 50 by thinking about what the future is going to look like and thinking differently about the rich and the poor. Now, in one study, we did a survey of experts, and we asked them differently. We asked them, what do you think about delta? What do you think about G? What do you think about eta? And we took kind of averages of these numbers, and that motivated our choice of discount rates in that paper. Right? Nordhaus had higher values. Our median view here gave somewhat lower, and Stern. Who's heard of Nicholas Stern? The Stern Review? Nobody? Let me tell you, you should have heard about it because it was super important at one point, about 15 years ago, when the British government decided they would figure out whether climate change was important or not. And they asked Nicola Stern, Lord Nicola Stern, to do a study for them. And he used a discount rate of 1.4, and eventually came out to the conclusion, and this was a secret, he kept it nicely secret. So actually the environmental movement thought that Nick Stern, who's a conventional economist, he was going to come up and say, no, climate change is no big deal. And in the end, there he is. The study is presented. He sits between the Prime Minister and the Minister for Finance, or the so-called Chancellor of the Exchequer in England. And he presents the study and says that climate change is extremely dramatic. And the main reason for that is choosing a low discount rate. That is, caring a lot about the future. Now, this is one of the few times I could use my name. I published a paper called an Even Sterner Review. And in that, I introduced relative prices. So let me tell you what I think about the future. We need to know what we believe about the future. So I'm conflicted about this issue of whether I think we can have eternal growth. And as you saw, we had one paper there where we said that we can have a bit of growth, but we're only until we get like 10 times richer, then it stops. And Ken Arrow, who's the most famous economist, he's even more famous than Martin here, the most famous economist around, now dead, he said, no, you can't assume that there are limits to growth. Human imagination is limitless. We talked a lot about this, and we agreed earlier concerts can always get more beautiful, paintings can get more beautiful, computer games can get funnier. Non-trivial examples include healthcare. We could all have fantastic healthcare. That's an enormous sector. You know how much it costs to be sick. Oh, we could have better medical diagnosis and treatment for everyone in the world. That's a gigantic sector, which could grow through technical progress. But if we have all that, notice I didn't say anything about having more cement and steel. We can't have infinite growth of some steel and cement in the world because it's a finite globe. So if we have growth, we're going to have structural change. And people, I don't know if any of your friends talk about limits to growth or negative. Degrowth is, I think, a sort of a rallying call for some parts of the environmental movement. They say we should have degrowth. And so there's some people, some environmentalists are very interested in whether we have growth or not. I'm going to tell you, it doesn't matter. It's not the average growth that is important. It is the composition of growth. It is what grows. And it's fine if medical analysis and technology grows, and we get better medicines and diagnosis and stuff. It's not quite so good if fossil fuels grow, because we'll be in trouble with the atmosphere. So it's the composition of growth that matters for the environment. And that, in economic terms, means that relative prices play a gigantic role. And you effectively have different discount rates in different sectors. And I showed that in, this is the amount of carbon dioxide that you would emit. And with a couple of different studies, this would be basically Nordhaus kind of, you see, it's not growing exponentially, it's kind of eventually tapering off a little bit, but still a lot of big emissions. This was Stern's recommendation for the world, and this was ours, not using an artificially low discount rate, but instead using different discount rates for different sectors, and saying that nature itself, coral reefs, forests, atmosphere, that is never going to grow. the best thing we can help for is a growth rate of 0. That is, that we don't destroy it. Otherwise, it's a negative growth rate we're looking at. But it's not going to have a positive growth rate. The production of mobile phones, cheese, wine, and other goods, that can be positive. But some sectors have to stop growing. I'll skip methane for the moment, if you don't mind, and say that through these series of steps of analysis, we explained the whole difference between 4 degrees being optimal and 1.5 being optimal. It's not like saying that we proved that we were right, but it's saying that we can at least identify the different model components and then talk about them sort of one by one. 5 minutes left. I'll speed up a bit and say that recently more friends of mine have a wonderful study where they have done more surveys looking at what factors they think should be included, and I thought I had more time, so I'll skip a little bit of that as well and say, yes, I'm not too far from behind what I wanted to be, I think, but say that this is hard, even if you try your best to do it properly. Then, of course, there are a lot of people who just say that it's not fair to tax gas, and you can close down the EPA and the OMB and a few other things, set the social cost of carbon to $1 and start drilling. So higher fuel prices have effectively a lot of enemies and very few friends. A few people sort of think that, yeah, we do need to tax carbon, but the leaders of oil-rich countries, several of them, they don't think so. Social, political scientists typically don't think so. They think it's a silly economist idea. The middle classes in Paris tried to burn down the place because of gasoline taxes. And the same thing happened in Nigeria here. Some Indian colleagues of mine, they say, what's carbon taxes got to do with sustainability? So there's multiple enemies of carbon taxes, which is one of the reasons why this would be possible to solve, but we probably won't. And partly that's because of people focusing on fairness, but I think they're focusing on the wrong kind of fairness. They're talking about whether higher oil prices are going to be fair to the middle classes and the lower classes and to this country or to that country, instead of talking about how fair the damages are going to be some people are suffering damages already, like the wildfires and the hurricanes and so on, but it's mainly going to happen in the future. Now, I got 2 slides, just show you one slightly different line of research here. What happened when Trump was elected the other day? We have looked at the reactions on the stock markets of the world for different companies. Oil and gas companies in the US did fine. Basically, stocks rose. However, not the oil companies in other countries. And oil in particular is a sort of a cartel kind of activity where OPEC and other countries are coordinating. And I think there's going to be conflicts within the group of oil producers. The US drills more. This is going to depress the price. And then others will retaliate by also drilling more, and maybe that will create an interesting set of problems. When it comes to renewables, we saw the opposite reaction, perhaps not surprisingly. And this is, I'm doing this work together with a friend called Samson Mukanyari, and we've looked at many multiple events and earlier elections and the signing of the Paris Agreement and so on. I should say that what happens on the election day or that week is not always representative of what happens afterwards. And if you look through the whole past Trump presidency, coal shares did very well when he was elected, then they actually continued to fall much more afterwards. So the story there is pretty complex, and I could have told you more about that, but there's one more word I want to say. Actually, I'm kind of finished there, but would you let me have another 3 minutes? Great. Because I think there's maybe a question hanging in there: should we be complacent about this and say, well? I think there's a lot of people who are complacent and say that, well, whatever, doesn't matter and we can't do anything about it. And there's other people who think that Armageddon is around the corner and that we might as well give up or commit suicide or do something. Everything is lost. And it's hard to navigate between these. And I was recently in Florence. It is the epicenter of medieval art. There is so much medieval art. It is in Florence. And in 1966, this happened. The Arno River flooded. There was like 15 meters of water everywhere inside all the Uffizi and the museums and the churches and everything. And everything was basically drowned, all the art. And there's two things I wanted to say about this. First of all, that it turned out that what is left is still a treasure. And it also turned out that with money and technology, you can save quite a lot. This is the birth of the art conservation. Art conservation was kind of born. I happen to have a cousin who's an art conservator in Spain. He went to Florence to train. Everybody goes to Florence to train. That's where everything happens. They learned the hard way here. And this is the Vasari's Last Supper. It is now almost perfectly restored. So are works of Leonardo and Filippini Lippi and Botticelli, many other people. So the conclusion is we too risk losing priceless treasures. It is tragic if there'll be no more skiing, for instance, no more snorkeling on coral reefs. It's tragic. But it's not Armageddon. A lot of people live lives without skiing and without diving on coral reefs, and they just look at their cell phones all day, and they have fun too. There are other things to do. We shouldn't move to Mars. We shouldn't give up. We should fight for a better and more sensible policy so that the loss is minimized. It's still worth fighting. There's a lot. We are not at Armageddon yet. We have a lot more to fight for. And if I may, don't be too angry if the price of gas goes up. Just buy yourself electric cars and solar cells. Thank you.
We have time for a couple of questions.
Thanks very much, Dr. Sterner, for your talk. Just on the policy area, I think the typical economist recommendation is to institute some form of carbon pricing, maybe tying it to an estimate of social cost of carbon. But that doesn't seem to be gaining much traction around the world, here or elsewhere. If that's the context, what other kinds of practical policy directions do you think would be most promising to pursue?
Thank you. I think that the other second, perhaps first most important other policy is to facilitate in various ways for various kinds of renewable and other alternatives and efficiency investments and battery investments. Now, there's a whole package of things, transmission lines that are more efficient and so on, things that can be done to speed up. Broadly speaking, this planet has been kind of lucky that solar cells and wind power works quite well, and they've seen rather rapid technical progress. But that has been partly the consequence of determined policy in a number of countries. First Spain, later Germany, later China, India, and the US under Biden, have put enormous emphasis on subsidizing various kinds of alternatives, and that's not enough in itself. If you do that only, then you get more renewables and still the same amount of coal, oil, and gas, basically. So it doesn't, but of course it makes it easier to then phase out the alternatives.
Thank you.
Other question?
Okay, so my son-in-law came for Christmas, and he's in graduate school studying environmental sciences. And he was all excited about nuclear energy and all the new technology. And of course, I'm in my 70s, and I'm horrified by this. And I think we should go solar and wind and all that. But does he have a point?
Well, if the nuclear industry doesn't make a comeback now, then of course they never will. We're in such a crisis of fossil fuels. It's a very logical thought. I've always been a little skeptical because there are some big safety issues and nuclear waste issues. And I should say I don't actually necessarily think that there's a lot of people focus on the long run problem of nuclear waste. I think that might be the wrong focus. Before you never, so far experience, you never get to the long run deposit. In the long run depository, you sort of ceramify the waste, and then you put it inside lots of copper and gold and 500 meters down and cover it in clay. And it's still not safe forever, but it's much safer down there than what happens. In the meantime, when you don't do that, you keep them in swimming pools next to the reactor. So in the reactor building, they're kind of protected by a big reactor building. And maybe that's not enough if terrorists come along. But the worst thing is actually these temporary waste storage, the short-run waste storage. That's not protected at all. It's just in a swimming pool. And that's what caused most of the problems in Fukushima. So I think two things have happened. One is that terrorists have turned out to be nastier than we imagined. I was very active in the nuclear debate in the 1980s, 70s and 80s in Sweden. We had a referendum. We never imagined that terrorists would blow up plants. I think today we realize they would. And Russia has in fact been fighting military battles inside Ukrainian nuclear power plants. And so, I mean, they seem fully capable of doing that. So I think that that's a new argument against nuclear power, is that they're not really terrorist-proof, war-proof. And the other argument is they turned out to be very expensive. They are more expensive, not just more expensive, they're like 10 times more expensive than solar power and wind power. Now, if solar power and wind power, you actually have to think of battery backup, other there's some extra costs that come along with that. So that complicates the picture, and then it depends on which country you're in and what the grid looks like and so on. But still, nuclear power is both expensive and kind of dangerous. So I don't think it's going to play a major role, but there might be some nuclear expansion. As you can guess, I don't like nuclear power very much, but I do think the climate problem is the big, long-run one. It is the bigger problem. Still, in spite of that, I don't think that nuclear power is really a very attractive option. But there could come new technologies. Fusion, for instance, doesn't have any waste problems or radioactivity problems or any such problems. It only has the problem that it's always 25 years away from but if it happens, it would be great. And maybe there could be other designs, but I mean, there's some excitement at the moment about small modular reactors. But I'm not convinced. I think the security problems of lots of small reactors everywhere will also be quite substantial. But I don't know. It's a big topic in itself. I don't think it's a big one.
You've addressed nuclear, but if you take the other two alternatives to fossil fuel, wind and solar, and let's say you stripped out subsidies, but you added in the cost of intermittency and backup, how close are they to being cheaper than oil as it's priced today?
I have one friend who, I wish he was here. He's also called Thomas Korberg. He's been the chief Swedish energy regulator, and he's a prominent professor who works in Japan, China, Sweden, everywhere. He's very optimistic about this and says that they are very getting to be more and more commercially attractive. It depends, again, which country you're in. Most places are kind of more like Arizona than like Sweden. Right? In Arizona, basically, the sun comes back every 12 hours. Right? Batteries wouldn't have to store for a very long time. That's true of India and Africa and lots of places. Sweden, it's actually not true. The sun goes away for 6 months. That's when it's kind of cold and we're indoors. We need the heating and so on. So we have some storage problems. On the other hand, those areas like Sweden and Canada and so on, they happen to have wood and hydropower typically, and wind. So, yeah, I mean, their solutions will look different in different places. And every kind of energy production has its problems. I don't want to deny wind and solar have problems. I think it still looks like we're lucky and they have smaller problems than everything else. Even if you count the batteries, and then you have to buy cobalt mines are never going to be nice. Maybe some of the countries that sell cobalt aren't nice either. And so there are problems. I mean, but I think there are smaller problems than the ones associated with nuclear power and certainly smaller than the fossil fuel cycle.
I think we've run out of time for questions, but if you'd like to speak with Professor Sterner at the reception, please join us. And let us join in thanking